Now, let's talk about how to calculate efficiency. Now, what we've got is a really simple formula. It looks like this. It says that the percent of efficiency of something is equal to the output energy in joules. Now, it doesn't have to be joules. Let me just make this clear. You just got to make sure that the output energy and the input energy are expressed the same. You'll see what I mean in just a second. The output energy divided by the input energy, now we are talking about energy, times 100. And the best way I can think to tell you about this is with the example of a mark when you would calculate your percentage in school. So if you got 9 out of 10 on a quiz, you would say you got 0.90 or 90%. It's the exact same thing. The total you could have gotten was 10 and you got 9 out of them. Input energy works the exact same way. Let's just say our input energy was 10. Now, we can't have more than 10. Remember, no system is 100% efficient. And so the number we're always going to get is going to be a percentage lower than 100. And so let's just say it was able to convert 9 of those units, let's say joules for now. 10 joules of input energy, and what it actually outputted when it transformed the energy was 9 joules, which meant that this system is 90% efficient. So let's do this in a problem that you might actually have to solve. So let's go over here. This is our practice problem number 1. Let's do this. Let's read through it together first. So it says Jack pedaled up a hill. So he's going up, so here's a hill, like that. I always love to draw it, and gained a vertical distance of 25 meters. So that means that from here, to the bottom of the hill, is 25 meters. Then he turned around and coasted down the hill, reaching a speed of 13 meters per second at the bottom of the hill. The combined mass of Jack and his bike is 68 kilograms. What was the efficiency of the transformation of his gravitational potential energy into kinetic energy? So there's two things happening here. Jack goes up the hill, and as Jack goes up the hill, at the very top, he's gaining gravitational potential energy the whole time. So e.g., when he gets to the top of the hill, that's the max that his gravitational potential energy is going to be. And then he starts coasting down the hill. And at the bottom, it is all kinetic energy. All right? Now, same type of problem that we did before with a pendulum and all the hill things. This is really similar. So let's go ahead. What do we know? Always write out what we know. So the delta H, the change in height, is 25 meters. All right? The mass of Jack is 68 kilograms. His velocity, or speed at the bottom of the hill, is 13 meters per second. So, and our G, our acceleration due to gravity, is 9.81 meters per second squared. So for this one, it's asking us to calculate the efficiency. Now, in efficiency questions, what we know is that this is not a perfect system. We cannot just say that EG is equal to EK. That doesn't work in this scenario because there's going to be loss due to friction and to heat. And so what we're going to do is we're going to calculate both of them. We're going to calculate our gravitational potential energy first. So let's go gravitational potential energy. There's our formula. Our mass is 68 kilograms. Our acceleration due to gravity is 9.81 meters per second squared. And our height, our delta H, is 25 meters. So let me just pull up my calculator here. Okay, so let's switch over here so you can see it. Here is my scientific calculator. I'll zoom in a little bit just so it gets a little bigger for you. And so I'm going to go ahead and calculate that. So 68, that's his mass, times 9.81 81 times 25, enter. So that gives me a energy, gravitational potential energy, of 16,667 joules. All right, so that's step number one. We've calculated that. Now we want to calculate our kinetic energy at the bottom, which is 1/2 mv squared. So 1/2, we know his mass, which is 68 kilos. Our velocity at the bottom is 13 meters per second, and we're squaring that whole thing. So let's go back to our calculator here, and we're going to punch this in. So we're going to go 1/2 times 68 times 13 meters per second, and that gets squared, and that gives us an kinetic energy of 5,746 joules. So put in our answer there. Let me turn off my face for a second here so you guys can see the whole thing. Perfect. So that's what we've got. Now it asks us to calculate the efficiency, and here's the formula for efficiency. Our percent efficiency is equal to the output energy divided by the input energy times 100. So here's what we have to decide. We have to decide which one of these two things, so this guy here, gravitational potential energy, or kinetic energy, we need to decide which one is our kinetic energy, or which one is our input energy, and which one's our output energy. So I'm going to give you two tricks to do that. Trick number one, the first thing that we're going to look at is we are going to look at which one is smaller. So let's take a look here. This guy here, our kinetic energy at 5,746 joules, that is smaller than this guy. Think about it as a test. It's really hard for you to get 11 out of 10 on a test, right? So the smaller number is almost always your output energy. But we can do this another way. Let's check another way. We want to know the efficiency of the transformation from gravitational potential energy into kinetic potential energy. So this first one, this is our Sorry, you lost me on audio there. My camera just died. That's why you don't see me anymore. So the gravitational potential energy, that comes first. That's our input energy because that's what we started off with. And we converted it from gravitational potential energy to kinetic energy. So that is our output. So now we can plug them in. We know that. I'm going to put this over on the side here so you guys can see it. So let's go here. So our output energy, so OE, output energy, is our kinetic energy. And our input energy is our gravitational potential energy. So now what I want to do is I'm just going to fill out my rest of my formula. So I say that my percent efficiency is equal to my output energy, which is 5,746 joules, divided by my input energy, which was 16,667 joules. Notice that joules and joules cancel. All right, so joules and joules cancel, which means that, times 100, which means that I'm going to be left with just a percentage. So let's do the math on this one. Here's my scientific calculator. We are going 5,746 divided by 16,667 667, and then we're going to multiply that by 100, and I get an answer of 34.475%. And now we look at significant digits. I've got 2 significant digits on everything, so I'm going to leave this as 2 significant digits. So my answer is 34, ooh, you can't see that. My answer is 34%. Down at the bottom here. So I multiply those together, that gives me 34%. So my overall efficiency of this particular system is just 34%. So even as he's coasting down a hill from the top to the bottom, the efficiency of that system is 34%. So we're going to try a bunch of examples here. On each example, in the bottom right-hand corner, there is the answer, which is just a screen grab of my work. And then there's a full video explanation. So if you ever get stuck, you can go to the video explanation and find out how to do it. Good luck, you guys.